Okay, so we start with lecture 3. And the first thing will be to calculate Moore-Penrose inverse of a general matrix A. So case 4, in the calculation of the Moore-Penrose inverse. For short, I will call it MP inverse from now on. So case 4, we have a general matrix A with n rows and m columns, and we will calculate A plus. For this aim, we will need the singular value decomposition of A. You probably know it from linear algebra, but we will recall what the singular value decomposition for a matrix A says. So theorem Cvd singular value decomposition or Cvd for short from now on. So we have matrix A as above, and we claim that A can be expressed as the product A is equal to U times sigma times V transpose, where U is a n times n orthogonal matrix. So if you recall what's orthogonal matrix, one of the characterization of orthogonal matrices is that U transpose is equal to U transpose U is equal to identity. But in words, this means that the columns of the matrix U are of norm 1 and perpendicular to each other. So the columns of U are an orthonormal basis for R to the power of n. This is equivalent way of stating that U is an orthogonal matrix. So this is true for U. Then V is also orthogonal matrix, but of size m times m. And sigma is a diagonal matrix. Sigma is the same of the same size as A, so m times m, and it is a diagonal matrix. That's why we had in case 3, so the case of a diagonal matrix, which was denoted with sigma, so last time. And let's denote this sigma with, so let's write sigma is diagonal matrix with diagonal entries sigma 1, sigma 2, sigma r, and then some zeros. And usually we order those sigmas in the decreasing order. So it's not necessarily true, but we usually do it. So sigma 1 is bigger than sigma 2, is not smaller than sigma 3, and so on, up to sigma r. And those are all positive. So those sigmas are all positive, and we call those sigmas singular values. So sigmas, sigma I is a singular value of A. And if we write U So if we write U and V in the column notation, we will use this a lot in what follows. So if we write U in this column notation, U1, U2, and U, we have n of them, and V as V1, V2, and Vm, because we have m of them. Then those U's are called left singular vectors. And those V's are called right singular vectors. So left singular vectors. And V's are called right singular vectors. Okay, so this is the singular value decomposition of A. So A can be expressed as the product of three matrices, U times sigma times V transpose. U and V are orthogonal matrices, and sigma is a diagonal matrix. And why would one do this? Because it's much easier to compute. So AX, it's much easier to compute AX in the following way. So to compute is as U sigma V transpose X. And since U and V are orthogonal matrices, this will also enable us to do some proofs and to see why A plus is very important when solving linear systems. So thinking with proving with by using singular value decomposition will make things clearer. Okay, and now let's recall how we calculate this singular value decomposition. And before writing the algorithm, let's see the idea behind. So idea behind the algorithm for computing CVD is based on few calculations. And let's make those calculations. So first, let's compute A transpose A. So let's assume, so here we will assume, that A is equal to U sigma V transpose. We don't have U sigma and V transpose. Now we are calculating the candidates for U sigma and V transpose, and the following calculations will give us an idea how to get sigma, how to get U, and how to get V. So you can think as U, sigma, and V as unknowns. But we require that they are U and V are singular, are orthogonal, and sigma is diagonal. So we assume that A is the product of those three matrices. And then let's calculate first A transpose A. So A transpose A, this is U sigma V transpose. And we have to transpose everything and multiply by U sigma V transpose. And so how do we transpose? We already did this a few times. So transposing the product of matrices is then the product of transposes in the reversed order. So it's V transpose transpose, which is just V. and then sigma transpose, and then U transpose. This is, so I transpose the first bracket, and then I just rewrite the second bracket. And what I notice here is that I get the product of U transpose and U, for which we know that our assumption is that it's orthogonal matrix. So U transpose U must be identity. And so we can forget about this middle term, U transpose U. And what remains is here in the middle is sigma transpose sigma. But for this sigma, we assume that it's diagonal. And let's write it in this form. So let's write here, we will use that sigma is some diagonal matrix 0, 0, 0. So this sigma, this S is of rank R. So it's R times R, and it's of rank, it's of full rank. And those zeros are zero matrices of appropriate dimension. So this is M minus R columns and N minus R rows. So it's block matrix with blocks S0, 0, 0. In this decomposition, sigma transpose S, sigma transpose sigma is just S squared 0, 0. So, and this S squared 0, 0, 0, this is just sigma 1 squared, sigma 2 squared, and so on, sigma R squared, and then zeros. So we denoted the diagonal elements of this capital sigma as sigma 1 up to sigma R. So then the diagonal elements of sigma transpose sigma are just their squares. So what does this tell us? So let's write this in a compact way. So then we get V, and then we get this sigma squared 0, 0, 0 matrix, diagonal matrix, V transpose. So what can we infer from this calculation is that the singular values of sigma are exactly square roots of the eigenvalues of A transpose A. So we have a matrix A. We calculate A transpose A. This is a symmetric matrix. And here we have the decomposition of this symmetric matrix into V times diagonal matrix times V transpose. And this means that the eigenvalues of this matrix are exactly the elements on the diagonal of this middle matrix. And the eigenvectors are just the columns of V. So here we see the idea how to calculate the Cvd decomposition of A. So we can calculate A transpose A, calculate its eigenvalues, and from those eigenvalues, just take square roots and get singular values of A. And if you also calculate the eigenvectors of A transpose A, then we get the columns of V. So now we have the candidate for sigma, we have the candidate for V, and how to get the candidate for U. So does anybody see how to then extract the candidate for U? What should we do? Yeah, rotate. So just swap A and A transpose. Yeah, that's true. So if we do the same with in the other direction, so doing the same calculation for A transpose, we get A transpose is U. You can do it by yourself, but we get U, and then here S squared 0, 0, 0, and U transpose. Of course, you have to just be careful here. So this middle matrix and this middle matrix are not exactly the same. So they are in the left upper corner is the same, but those dimensions of 0 are different, because this is so this matrix is so here we had sigma transpose sigma, so this was M times M matrix, but here we would have sigma times sigma transpose, and so this would be N times N matrix. So the difference between those two matrices is in the dimension of the zeros. So the difference is only in the dimensions of 0 blocks. Okay, so we either calculate A transpose A or A transpose, and from both of them we can get singular values. So we calculate one of them and calculate singular values, because they are just square roots of the eigenvalues. And so the columns of V are then right singular values, and the columns of U are left singular values. However, we cannot just calculate both of them and then put them in any order. We have to be careful, a little bit careful, because if those singular values, if we have two singular values which are the same, so if let's say that sigma 1 is equal to sigma 2, then it's important that we take here V1 and V2, and then the corresponding U1 and U2. It's not unimportant, so the order. So this means if two singular values are the same, this means that the eigenspace of the so the eigenspace of this eigenvalue sigma 1 squared is two-dimensional, and there are many choices of two basis vectors for a two-dimensional eigenspace. That means that when we fix V1 and V2, then U1 and U2 are not arbitrary. So they are dependent on V1 and V2. So once we fix V1, V2, now we have to be careful how to choose U1 and U2. And the following calculation will tell us how to choose U1 and U2. I mean, how to calculate U1 and U2 once we have V1 and V2 fixed. So what we know, just let's write what we know. A transpose A, Vi. This is just sigma I squared times Vi by construction. For every, so this is for I smaller than R. And A transpose U J is again by construction just sigma J squared times Uj. This is for J smaller than R. Otherwise, so other vectors are unimportant. Okay, so we know this, and now let's calculate A transpose A. Let's say on let's say that we will calculate the other direction. So A transpose on A VI. So what we do here, we take this matrix A transpose, and we would like to calculate the candidate for UI, and the candidate would be AVI. So this is the candidate for UI. For UI, and of course AVI. So if VI is is of length 1, it doesn't mean that AVI will be of length 1. So the length will change. So this will be the candidate for UI times some constant. And we will see that this is the proper candidate, and we will also see what this constant is. So let's do this computation. We have A transpose AVI. Now I just got rid of brackets because matrix computation is associative, so we can put brackets in any order we want. And now I will try to use that VI is an eigenvector of A transpose A. So I will use this one. And I get A times sigma I squared VI. So this is sigma I squared AVI. So what I got, if we look at the beginning, so we have this matrix A transpose, and we computed the product A transpose with the vector AVI, and what we got was the same vector AVI just multiplied by some constant, and this constant is exactly the eigenvalue sigma I squared. And this means that AVI is an eigenvector. So it means that AVI is an eigenvector of A transpose corresponding to the eigenvalue sigma I squared. And this basically solves what I said before. We find V's. So V is the VI is the eigenvector of A transpose A, corresponding to the eigenvalue sigma I squared. And how to calculate UI? So UI is then just AVI. This will be really the eigenvector for the eigenvalue sigma I squared for this reversed matrix A transpose. But of course, we want that it's normalized, so it's of length 1. So the proper candidate, we just normalize AVI to get UI. So this UI is AVI and multiplied by 1 over the length of AVI. So this gives us then U's. And in fact, if you look, what's this? So this AVI, 1 over AVI. So we will use this further. So let's calculate the norm of AVI. So this AVI, it's just, so So AVI, it's just sigma I squared, sigma I squared. And if we use this here, we get sigma I AVI. So the square of the norm is sigma I squared. That means that norm is sigma I. So if we use this here in this equation, then we get sigma I times AVI. So the algorithm just a moment. So times are divided by, let's look again carefully what I wanted to do this to do here. Yeah, of course, divided by you are correct. Thank you. So once we have VI, then we calculate AVI, and we don't need to calculate again this Euclidean norm. We just do this, we just think about this and see that norm of AVI will be exactly sigma I, which we already know from above. So here we just multiply by 1 over sigma I. Okay, let's extract now the algorithm for computing CVD. So we choose A transpose A if N is so A transpose A if N is bigger than M. Otherwise, A transpose. Why we do this? Because A transpose A will be then smaller than A transpose. And what we do, we calculate the eigenvalues of A transpose A. Those are sigma 1, lambda 1, lambda 2, and so on, up to lambda r, and then some 0 eigenvalues. So we calculate the eigenvalues and the corresponding eigenvectors. Those are V1, V2, up to VR. So this V1 corresponds to lambda 1, V2 corresponds to lambda 2, VR corresponds to lambda r. And the other eigenvectors are just the basis for the kernel. And we will see shortly that they are not important. I will write them here in the long algorithm, but you can forget about them. Okay, this is what we do, and we form the matrices sigma, which is just diagonal matrix with square roots of the eigenvalues on the diagonal. And this diagonal matrix, you have to take it of appropriate size. So it's the same size as A. So it's n times M matrix. And we form V. So V is V1, V2, where V1 is a matrix of those eigenvectors which correspond to non-zero eigenvalues. And V2 is the matrix with columns which correspond to the eigenvectors which are in fact the basis for the kernel of A, transpose A. So A transpose A. Okay, so we have lambdas, we have V's, and now we have sigma. We build sigma out of them, and we form V out of them. We decomposed V into this V1 and V2 blocks. This will be clear soon why we do this. And it only remains to calculate U. And based on the computation above, we know that U is then just, so we take U1 is A V1 over norm of A V1. We know that A norm of AV1 is just sigma 1. And we do this also for the other I. So U2 is AV2 over sigma 2 and so on. UR is AVR sigma R. So these are the left singular vectors corresponding to non-zero singular values. And then we just complete the set U1, UR to the orthonormal basis for R to the power of n with n minus R additional U's with UR plus 1, UR plus 2, UN, and form the matrix U as, again, U1, U2, where U1 consists of the vectors we calculated from V's, so U1, U2 up to UR, and the block U2 consists of those completed vectors. So those vectors used to complete the set U1 up to UR to the basis for R to the power of n. And how to get A? Then A is just U times sigma times V transpose. And this is the singular value decomposition of A. Is there maybe any question? Was this clear?
Yes, I have a question. Why have we divided U and V to U1 and U2?
Why we decomposed U into U1 and U2?
Yes.
This is the question. Yeah, and this is a good question. Yeah, here in this algorithm, we could just left this U1 and U2 and V1 and V2. It just makes a mess. But why I did is, now let's do this optional point 3 star. A, it is also true that A is equal to U1, and then S and V1 transpose. Okay, I haven't defined S in this algorithm, so where S is diagonal matrix with non-zero singular values on the diagonal, so sigma 1, sigma 2, up to sigma r. And this is really a square matrix. So it is also true that A is just U1 S V1 transpose. So we don't need these U2 and V2 blocks. And it's really easy to check this. Let's check 3 star. So by construction, we know that A is equal to U sigma V transpose. And now I will use this block decomposition. It's U1, U2. And this sigma is S in the left upper corner, 0, 0, 0. And here we have V. Again, I will decompose V into this block decomposition, V1 and V2. And when we transpose, we get V1 transpose, V2 transpose. And it remains only to calculate this product of 3 matrices, and we will see that we get just U1 S V1 transpose. So if we first multiply those 2 matrices, we get U1 S. So this is first row and first column. And then first row and second column is just 0. And it remains just to compute this product, and we get U1 S V1 transpose. So it's U1 S V1 transpose. This is why I did this decomposition, and also in the proofs which follow in the second and third hour, this decomposition will be useful.
Okay, thank you.
Okay, thank you for the question. So if we look again at the algorithm before we end this first hour, I will use another color. So we calculate lambda 1 up to lambda r, so those eigenvalues in the first step, then the other eigenvalues are 0. And we calculate V1 up to VR, and we don't need to calculate the kernel of A transpose A, so not needed. So this vectors Vr plus 1 up to Vn are not needed. So in fact, we also don't need this V2 block. And in the second step, we really need only those U1 up to UR. And again, we don't need to think about completing the set to the orthonormal basis for R to the power of n. So how would we do this? First, we would choose n minus r linearly independent vectors from U1 up to UR, and then we would do Gram-Schmidt algorithm. So it would require quite a lot of work to complete this set to the orthonormal basis, but we don't need to do it, so not needed. And so we don't need to do, no need to do step 3, but only 3 star. Okay, is there any question? So before we continue, just to persuade you a little bit more about this step, probably this was quite quick. So let me again explain why this is true. This UI is AVI over the norm of AVI, and here I claim that the norm of AVI is sigma I. So I would just like to give you another reason why this is true. So what we know, what is the norm of AVI? So the norm of the vector, it is just the square root of the product of components. It's the Euclidean length. So it's the square root of the product of components. But how to get the product of components of the vector? So if we have norm of V, this is just square root of V transpose V. So calculating V transpose V just gives us the sum of the squares of the components of V. And I will use this here. So norm of AVI, this is AVI transpose AVI. And now again, transposing changes the order, and it's just the product of transposes. So it's VI transpose A transpose A VI. And here I use that VI is the eigenvector of A transpose A by construction, corresponding to the singular value sigma I squared, to the eigenvalue sigma I squared. So we get VI transpose sigma I squared VI. And this sigma I squared under square root comes out. So it's sigma I. And what remains is just square root of VI transpose VI. But by what I wrote here, this is just sigma I times the length of VI, but VI is of length 1. So what remains is sigma I. So this is just a short argument why for my claim that norm of AVI is sigma I, and I really don't need to compute AVI, norm of AVI in the algorithm again, because it's precisely the singular value, sigma I. Okay, this is what I wanted to add to the first hour. Okay, so now we know how to compute the Cvd decomposition of A. And we will use this to compute the Moore-Penrose inverse. So, and I ask you, what is the candidate for the MP inverse of A? So we have A is equal to, now I will need both facts. It's U times sigma times V transpose. This is the long one. And in short, it's U1 S V1 transpose. So what would you claim would be A plus? Conjecture. Would anybody try to guess? So again, we can think in the way that those would be square matrices, then A would be square, then U and V would be square, and sigma would be invertible. And if we take the inverse of this, it would just swap the order and invert each of these matrices. And since V is orthogonal, V transpose inverse is just V. Sigma inverse is just diagonal matrix with inverted diagonal entries, and U inverse is just U transpose. So this would be the case if A was invertible. If A is singular or if A is rectangular, then the same conjecture we can conjecture the same for A plus. So it's V transpose inverted, so it's V, then sigma not inverted but sigma plus, and U inverted, which is U transpose. And in the short notation, this would be V1 S minus 1 and U1 transpose. So this is our conjecture. So, and how would we prove this conjecture? What do we have to check? Yes, so we have to check the conditions in the MP inverse of A. So one of them was, let's start. So we have to check. So we have to check 1 to 4 in the definition of A plus. And let's do 1 and 3, and 2 and 4 are analogous, and you can do it by yourself. So 1, we have to check that A plus is the generalized inverse of A. So A plus A is A. This is the first thing which we have to check. And let's just calculate. So A is U sigma V transpose. And our candidate for A plus is V sigma plus U transpose. And A is U sigma V transpose. And we start calculating. So what we get is we get rid of those brackets at first step. And what we notice here, we get V transpose V. So this is identity. and U transpose U, this is identity. So you may wonder why I wanted to do those calculations in the long notation. Here you see, if I already use the short notation U1S V12, V1 transpose, then here I will get V1 transpose V1, and V1 transpose V1 wouldn't be identity because it V1 transpose V1 is identity, and then it has some zeros. So I would need to be a little bit more careful when doing this calculation. That's why I rather calculate in the long notation, and at the end I will just argue that this product V sigma plus U transpose is just V1 S inverse U1 transpose. So this is the reason here I couldn't cancel V1 transpose V1 in the short notation. So I will rather calculate in the long one. So what I get here is U, then sigma plus sigma V transpose. But what is this sigma plus sigma? What is this? The easiest argument without any computation. I could use one case from last hour. So we had sigma, and we already said that its Moore-Penrose inverse is sigma plus, which is just transposing and inverting the diagonal entries. And this means that here I get sigma as a result without any computation. So what I get is U sigma V transpose, and this is exactly our A. So this point 1 is okay. So this candidate for A plus satisfies requirement 1. Then the second one is analogous. So A plus should be A plus. It's analogous computation. So we won't do it. And the third, A plus A transpose should be A plus A. So A plus A should be symmetric. Let's do this computation. So A plus A, I plug A plus is V, and then sigma plus U transpose. And here I plug for A U sigma V transpose, and transpose everything. So what I get is, again, I will get rid of brackets inside this outer bracket. So V sigma plus U transpose U sigma V transpose. Here in the middle, U transpose U cancels out because it's identity. And what I get is V and then sigma plus sigma V transpose. But this inside the bracket is symmetric matrix, because so this sigma plus sigma, this is identity 0, 0, 0. And if I transpose this, it remains the same. So it's V and then this identity 0, 0, 0, which is sigma plus sigma V transpose. So, but I want to get A plus A. But here I can again put A transpose U transpose U in the middle to get A plus and A. So V sigma plus U transpose U sigma V transpose. but this is just V sigma plus U transpose, and then U sigma V transpose, so it's A transpose. I mean, it's A plus A. So also this third condition is fulfilled by our candidate for A plus. And you can analogously check the fourth one. So AA plus must be also symmetric, AA plus. So this is analogous to 3. So what we did here, we checked, in our conjecture, we checked that V sigma plus U transpose is really the Moore-Penrose inverse of A. But by the same calculation as above for A, the important part of this product is only this part, V1 as inverse U1 transpose. So we checked that this is the Moore-Penrose inverse, but a short calculation shows that only this part is important, V1 as inverse U1 transpose. So the algorithm for computing MP inverse. A plus. So step one, step two, step three from the Cvd decomposition of A are the same, 1, 2, and 3 star. So 3 star was this short, was the calculation of the short Cvd decomposition. So 1, 2, 3 star from the Cvd of A are the same. And in the last step, just calculate A plus is V1, and then S inverse, and then U1 transpose. And what you get is, what you get is M times N matrix. So this V1, this was M times R block matrix, and then this was S inverse, this is R times R, and this U1 transpose, this is R times N. So it's U1 has N columns, has R columns and N rows, and then we transpose, so it has R rows and N columns. Okay, and to make this more clear, let's do an example. So let's take the matrix A equal to 2 times 3 matrix with the first row 3, 2, 2, and the second 2, 3, minus 2. And we would like to calculate CVD of A. So calculate CVD of A and A plus. So if we follow the algorithm for CVD, we know that we have to calculate the eigenvalues of A transpose A or AA transpose. And my question is, what is easier in this case? do we use A transpose or A transpose A? A transpose. Yes, this will be easier because it has dimension 2 by 2. Yeah. A transpose, this is 2 times 2, but A transpose A is 3 times 3. So this A transpose A will have one eigenvalue which is 0 in comparison to A transpose. So they have A transpose, and A transpose A has the same non-zero eigenvalues, but A transpose A has also one zero eigenvalue. But we don't need it. So it's easier to do the computations with A transpose. And if we compute A transpose, so let's use Mathematica. You can get this Mathematica. Why I will use Mathematica? Because in the second step, where we will be using, where we'll be calculating eigenvalues, it will require symbolic computation, and Mathematica is better for symbolic computation compared to MATLAB and Octave. So we will use Mathematica for this example, and you can also get student's license for Mathematica. Just send an email to to IT Podpora, and you get license for Mathematica. So here I already did those calculations. Okay, only A transpose. I didn't do A transpose. So our A, this is the matrix 3, 2, 2, and then 2. It has a little bit different syntax than MATLAB. Probably you know Mathematica. So this is our matrix. We can write it in the matrix form to see that we really have the right matrix to work with. And then we calculate A transpose A. No, we said A transpose because it will be easier. So matrix form of transpose of A times A. Okay, this is the direction we don't want. So let's change the order. A transpose. This is our 2 by 2 matrix we get. So we have to calculate the eigenvalues. So if you remember, how do we calculate the eigenvalues? We have to subtract lambda times identity, or x times identity, and calculate the determinant. And the zeros of the determinant are precisely the eigenvalues of the matrix. So here I already subtracted x times identity, and then I calculate the determinant, and I'm searching for the zeros of this determinant. So I'm solving. The determinant is equal to 0 with respect to the variable x, and what I get is 9 and 25. So 9 and 25 are the eigenvalues. Okay, so the singular values are square roots of this 9 and 25. So the singular values are 3 and 5. But now I want to get u, and so u and v. So here I will calculate v. I will calculate v's. So I calculate transpose A times A. This is this 3 times 3 matrix. And I already know from above that one of the eigenvalues is 25. So that's why I subtract 25 times identity matrix and calculate the kernel. This is this null space, command null space. And I get a vector from the kernel, which is 1, 1, 0. Of course, in our algorithm, we have to normalize this vector. So we divide it with its norm. In this case, the norm is 1 squared plus 1 squared under square root. So it's square root of 2. We have to divide by square root of 2. I repeat the calculation for the other eigenvalue. So the other eigenvalue is 9. Again, calculate the kernel, which is 1 minus 1, 4. Again, by normalizing, I have to divide by the norm. And the norm is 1 squared plus minus 1 squared plus 4 squared, everything under square root, which is 18. So I have v1 and v2. And we said that we don't need the third vector in the singular value decomposition because the third vector corresponds to the eigenvalue 0. So I won't even calculate v3. And now how I get u1 and u2, I just map v1 by a. Here I had to use transpose of v1 because Mathematica returns row vectors instead of column vectors. So when we calculate null space, then Mathematica returns row vectors. That's why I had to use here transpose of v1. So I got 5, 5. This is the direction of u1. And at the end, I only normalize it so that it's of length 1. And the same for u2. So a times v2 gives me u2. Okay, and I will just write the results here, and you will also have them in handouts. So a transpose, this is 17, a 8, 17. Then the eigenvalues determinant of a transpose minus lambda times identity is 0 precisely when lambda is 25 or lambda is 9. So this means that singular value 1 is 5 and singular value 2 is 3. And then to get v1, we have to, v1 is in the kernel of a transpose a minus 25 times identity. And we got that this kernel is 1, 1, 0. So it's the vector 1, 1, 0. So it's the linear space. So the span of this vector. So linear span of this vector when 1, 1, 0, which means that v1 is the normalized one. So 1 over square root of 2, 1 over square root of 2. And the same for the other eigenvalue. So v2 is in the kernel of a transpose a minus 9 identity 3, which is linear span of the vector we had 1, minus 1, 4. And we have to normalize. So v2 is 1 over square root of 18, and then minus 1 over square root of 18, and 4 over square root of 18. So we don't need v3. And then U1 is just AV1 divided by norm of AV1. It is AV1 divided by, so singular value corresponding to the V1, so it's 5. And what we get is 1 over, so it's 1 over square root of 2 and 1 over square root of 2. So if you remember from Mathematica, it was 5, 5. But if we just normalize this vector, we get 1 over square root of 2 and 1 over square root of 2. And the same for U2. So it's AV1, AV2 over AV2. And if we calculate this, we get 1 over square root of 2 minus 1 over square root of 2. So this means that A is then equal to U, which is just U1 in the first column and U2 in the second column. So this is U1, U2. And then here I have 2 by 3 matrix sigma with eigenvalues on the diagonal. These are 5 and 3. And the last column is zeros. This is sigma. And then V. So consisting of, so this is V transpose, in fact. So this is V transpose. So I will, V1 was 1 over square root of 2, 1 over square root of 2, and 0. So this is V1 transpose. And then the second one was 1 over square root of 18 and minus 1 over square root of 18 and 4 for square root of 18. This was V2 transpose. And we didn't, we don't need V3, so I won't calculate it because I will never use it since it corresponds to the eigenvalue which is 0. Okay, so this is V transpose. And at the end, A plus, we said that this is V. So V1, A square root of 2, A square root of 2, 0, and then A square root of 18 minus 1 over square root of 18 and 4 over square root of 18. And we don't need the third column. And we invert sigma. So we get 3 rows and 2 columns. And on the diagonal, we have 1 over 5 and then 1 over 3. So this is sigma plus. And U transpose at the end. But U is, in this case, U is just U transpose. Because if you just transpose 1 over square root of 2 and 1 over square root of 2, it's the same. So U remains the same, but only in this case. So this is U transpose. Okay. And in fact, if we do this, if we perform now the calculation, what would be the calculation? It would be, so it's always like that. So I will show you. So we take this sigma 1, and we take V1, and we take U1 transpose, and we get so 1 over 5 times the matrix V1 U1 transpose. So this is a matrix. This is 3 times 2 matrix. And then we take the other singular value 1 over 3 and the second column of V and the second row of U transpose and get plus 1 over 3 times V2 times U2 transpose. It's the second 3 times 2 matrix. Both of those are of rank 1, both of those matrices, so this is rank 1 matrix. And this is also rank 1 matrix. And if there would be another eigenvalue, then we would go on in this way. So we would take the third singular value and put it here and calculate the third column of V with the third row of U. So it's always the same. It's just you can think by yourself that matrix computation of this type is exactly what I wrote here. Okay, I can just write what we get at the end. So at the end we get 7 over 45 and then 2 over 45 and then 2 over 45 and 7 over 45 and the last row 2 over 9 and minus 2 over 9. Is there maybe any question? Okay, before we go to solving linear system AX is B with the use of this Moore-Penrose inverse, so it will be a special solution. We already know that if the system is solvable, so we have two possibilities. We have AX is B. This system can either be solvable or not. So if it is solvable, then GB is a solution where G is any generalized inverse of A. But we will see that A plus B is a special among those solutions. We will shortly see in what sense it is special. So this is the first case when B is really in the column space of A, when the system is solvable. But when the system is not solvable, when AX is B is not solvable, we will see still that A plus B is the best, so it's the solution using this method of least squares. So that the norm of what remains, so norm of B minus AX is the smallest among all possible x's. X, which is appropriate, is exactly A plus B. So these will be two properties why Moore-Penrose inverse is very useful. But before we do this, I will just mention the use of Cvd decomposition for the principal component analysis. This is one technique to analyze the most important parts of the matrix, and it can be used in many ways when we analyze big data sets and we want to extract what's the most important part of this data. We can use this principal component analysis. You probably know some about this analysis. You will do also an example on exercise sessions, and there will be also projects out of this topic. But let me briefly just tell you what it's about. So the use of CVD for principal component analysis. So we have our A is U sigma V transpose. We just saw that, so it can be written in this form. So the column decomposition of U, let the column decomposition of U be U1, U2 up to UN. And then sigmas are just sigma 1 up to sigma R and some zeros. But I will allow now that sigmas are also 0 so that I can go up to sigma M. Here I assume that N is bigger than M. So here N is bigger than M. And then we have V1 transpose. So it's V1 transpose and then V2 transpose up to Vm transpose. We can write this in this way. So sigma 1, so as I did before, so sigma 1 and U1 V1 transpose, and then sigma 2 and U2 V2 transpose, and so on. Sigma R and then UR and VR transpose. So this can be written as sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose, and so on, plus sigma N sigma M UM VM transpose. So those components are rank 1 matrices. And these sigmas are ordered in the decreasing order. And I also allow zeros. And now we have a big matrix. Let's say that N is really big. So we have a lot of columns and then a lot of rows, and then the number of columns is smaller, but we have a big matrix. But we want to somehow store this matrix with a small number of data. So we don't want to store all the information about A, only the most important part. And what we did here, so we decomposed A into the singular value decomposition, U sigma V transpose. And somehow we would like to just forget about those rank 1 matrices which are not important, which won't change. So if let's say that we would like to forget about those parts that don't change A a lot. So we would like to forget, for example, on sigma M part, and then if sigma M minus 1 is also small, then we want also to forget about this part, and so on. So we want to forget about those singular values that do not change, that are smaller, that are much smaller than all the other singular values, and don't change A a lot. And it really turns out that if we do this, we get the best possible approximation for A if you allow certain rank of matrices. So let me write this precisely. So we want to approximate A with the matrix of rank k. So we don't want, so k, we choose k much smaller than n and m. So we would like to approximate A as good as possible with some matrix of rank k. So as good as possible. So we would like that A is approximately B, where B is of rank k. Rank of B is k. And we want that this approximation is as good as possible. What do you think is the best choice for B? What would you conjecture would be the best choice for B? So you're allowed to take any matrix B of rank k such that B will approximate A as good as possible. So I will write soon what as good as possible means, but what would you conjecture would be a good choice? Yes, so we take only the k largest singular values with the corresponding singular vectors. So the best choice would be to take the first k summands in the singular value decomposition. So B is sigma 1 U1 V1 transpose plus sigma k UK BK transpose. And as good as possible, what does this mean? This means that A minus B, so this is some matrix, and the norm of this matrix is the smallest possible. When B varies, when B runs over all rank k matrices. Okay, we didn't talk about norm of a matrix so far, but there are more norms of a matrix. So one which directly generalizes Euclidean norm would be Frobenius norm. So we have, I will just tell you two specific norms of matrix. So there are more, there are many matrix norms, but one matrix norm is this one. So Frobenius norm of a matrix. It's direct generalization of the Euclidean norm of vectors. So norm of a matrix, we have a matrix Aij, Ij run from 1 to n, let's say, or let's stick to rectangular matrices. So I runs to I runs from 1 to n, and j runs from 1 to m. So Frobenius norm of this matrix is just sum of squares of the entries and everything under square root. So this is just double sum Aij squared when A runs from 1 to n, j runs from 1 to m, and we take square root. So we just square every entry of the matrix and we sum this everything together. We get this sum and take the square root. And this is one of the possible choices for the norm of a matrix. So here in the Frobenius norm, when we compare A and B, in the Frobenius norm, we are just summing up squares of the differences in every entry of the matrix. But this is one of the possible generalizations of the Euclidean norm to matrices. But the other one is so-called second norm of the matrix. So this is defined as A. So 2 norm of the matrix, or spectral norm of the matrix. This is maximum of AX when X runs over all norm 1 vectors. So this is the other possible norm of a matrix, but there are also many others. So 2 norm of a matrix, we just calculate norm of vectors AX when AX runs over the unit sphere, all vectors of norm 1. We calculate the maximum, and this also gives us some matrix norm. It turns out that those are different norms. So this Frobenius norm and this spectral norm are different norms. But what I wrote here in red is true in both of them. So it's not true for any norm that B is the best approximate of A when B runs over rank K matrices. So it's not always the case that we should take the first K singular values and corresponding rank 1 matrices, but it's true in those Frobenius and spectral norm, and this is what what's usually meaningful for us. So this is true. This holds in both norms below. So in the Frobenius norm of a matrix and in the spectral norm of a matrix. And we call those sigmas principal directions. So the biggest sigmas are called principal directions. And those, principal values, and the corresponding V's are called principal directions. And why are they important? Because they tell us something about our data. So if we have some data, put them in the matrix A, and would like to know what are the most important information about the data. So they are collected, especially they are precisely in those principal values with their corresponding principal directions. So in the lab session, you will see one example of the use of this. This is in fact the theorem that B, which best approximates A, is exactly this sum. So we'll see use of this when compressing images. So you get an image. The image is a matrix. In every entry of this matrix is some information about how much color is in the corresponding part of the image. So this matrix represents pixels of the image, and in every entry, the number tells us how much black. So what's the ratio between black and zero and white color in the image? And if you have a big matrix, you don't want to store the whole information about the image, only the most important part. And what you do, you can calculate the singular value decomposition of this matrix, and take only first few principal values and principal directions and get a good approximate of the initial picture. Of course, if you work with color images, then you need 3 matrices, one for each color, red, green, and blue. And you will also see examples of this in the projects. So you will have data, you will have the task to put the data in the matrix A and then analyze the data so that you use only the most important part of this data and you don't have to store everything about this data. Okay, are there any questions?
Yeah.
Yeah, you can ask. Okay, otherwise we make a break and continue in 15 minutes. Okay, let's start the last hour. So what remains in these linear systems is the connection of the Moore-Penrose inverse with solving such systems. So I will tell you both things which remain, and we'll see if we're gonna be able to prove both of them today, but you will be already able to use them on exercise sessions. So let's return, we return to our system AX is B, and A is n times m matrix. And there are two possibilities. So one possibility is that n is bigger than m, and the other is that n is smaller than m. And in the first case, we are talking about underdetermined system. Underdetermined. So n here is smaller than m, which means that we have less constraints than the variables. So less constraints than variables. And then the opposite direction is that we have overdetermined system. Which means that n is bigger than m, and this means that we have more constraints than variables. So every row of A is one linear equation, is one constraint, and every coordinate of X is one variable. And if we look at underdetermined system, we have less constraints than variables. In most cases, such a system will be solvable, and it will have infinitely many solutions. So let's say that we have n constraints. Generically, we could choose m minus n x's as we want and calculate the others. So generically, the solution will be m minus n dimensional. So generically, there will be infinitely many solutions. That is m minus n dimensional space of solution. While on the other hand, when we have more constraints than variables, there will usually be no solution. If those constraints are completely different from each other, then there will be no solutions. Generically, no solutions. Let's look at example for both. So in the first case, let's say that we take only one constraint, and let's say that we have two variables. What would be geometrically AX equals to B? What would be geometrically the system AX is B in this case, when n is 1 and m is B, n is and m is 2? So AX is B. This A is 1 times 2 matrix. This X is 2 times 1 vector. And this B is then just one, just real number. So then AX is B is only one linear equation, and geometrically it represents a affine line. So if we draw, we have this line AX equals to B. And every X on this line solves our system. So these X's, which are in fact pairs X1, X2, are our solutions. And indeed, we have one-dimensional set of solutions because, so we have here m is 2, n is 1. We expect one-dimensional space of solutions, and it really is. So this blue line is one-dimensional space of all solutions. But we would somehow, out of those solutions, extract the most important one, and usually we would like to choose the solution which has the smallest norm. And so this one solution where we get exactly right angle when we look at the angle between our set of solutions and the vector that connects the origin with this solution. So this is the solution of smallest norm. So this is the solution of smallest norm. So other solutions have bigger norm. Let's say this one is also solution. This one is also solution. This one. So all the others have bigger norm. And we will prove that this solution is exactly the solution of smallest norm. Is exactly A plus B. So this will be our theorem. If we have an underdetermined system which is solvable, which means that B is in the column space of A, then the solution among all solutions, the solution of smallest norm is exactly Moore-Penrose inverse of A times B. Okay, and if we use the same example on the other side, when we have this overdetermined system, still let us take that we have m is 2 and n is 3. Now we need more constraints than variables. That would mean then AX is B. So this A would be 3 times 2 matrix, then X would be 2 times 1, a vector, and B would be 3 times 1 vector. So geometrically, each row represents one affine linear function. So we have, let's say, the first row, this is A11 x1 plus A12 x2 is B1. And then the second row, let's say this is A12, sorry, A21 x1 plus A22 x2 is B2. And then the third, let's say is this, A31 x1 plus A32 x2 is B3. And we see that there is no X that would satisfy all three equations, because it would mean that those three lines intersect in the same point, which is not true. So we have three intersections, but each intersection is also is only solution for the intersection of two lines. But we would like to find the point in the plane such that the distances to all three lines are the smallest possible. So this distance, and then this distance, and this distance, we have these three distances. And sum of those three distances, we would like a point such that this the sum of those three distances is the smallest one. So we search for the point such that the sum of the distances is the smallest possible. And again, the theorem says that the solution to this problem is exactly A plus B. The solution that minimizes, so the solution which minimizes the sum of distances, I mean the sum of squares of distances, because we're using least squares method, the sum of squares of distances is A plus B. So instead of taking the sum of absolute values of distances, we take the sum of squares of distances, and the theorem says that A plus B is exactly the solution to this problem. So we looked examples of this. So we looked this theorem on two examples, but it's the same for a general N and M. So whenever N is smaller than M, we have an underdetermined system. Usually it's solvable. And among all solutions, the solution of smallest norm is exactly A plus B. And on the other hand, the overdetermined system is usually not solvable, but the solution that is the solution by the method of least squares is exactly A plus B. And let's try to prove those two theorems in the remaining part of this third hour. So we have 17 minutes to the end, and we will try to prove those two theorems. Let's say this is Theorem 1, and this is Theorem 2. So proof of Theorem 1. So what's our setting? AX is B. N here is smaller than M. And B belongs to the column space of A. These are our assumptions. And we would like to prove that that X is equal to A plus B is the solution. This is the first part which we want to prove. And the second part is that A plus B has minimal norm among all solutions. So one of the parts is something which we already know. And of course, the first part is the part which is easier and we already know. Does somebody see why we already know that part 1 is true? This is what we already know from lecture 2.
Can we multiply the first equation, so A times X equals B with A plus from the left side?
Yeah. We would get that that this is true, but since A plus is not invertible, we could change something. So if let's say that, I will show you why this is not completely correct. So if we have, for example, some system Gx is B, and then, so let's say that this is something, and then this is something. And when we multiply, for example, by some matrix which lives only here and has zeros here, then we would get, we would compare only the parts, only those two parts, the first few components of both sides. So it's better to write this in this form. So here it could also have something here. So when we multiply this with, if you multiply this with some singular matrix, we would compare only both sides on the image. But what's true on the, so what's true here, we would get that, okay, when we multiply this with this A, we would only compare, we would get here 0, we would get here 0, and then we would only compare those two parts of the initial vectors. But we wouldn't have any information about those two parts, because this matrix with which we multiplied had some kernel. So this is not exactly correct to multiply by matrix A plus, but we know from the topic of generalized inverses, we know that GB is a solution for every generalized inverse of A. So if we take A plus is in particular a generalized inverse, so taking G is A plus, then proves part 1. So we know that if we calculate any generalized inverse of G of A, then GB is a solution. and taking the specific generalized inverse. So MP inverse proves 1. And then what we also know, so to prove the second part, that all solutions to the system AX is B are of the form A plus B plus, and then we have something from the kernel of A, which is A plus A minus identity times Z, and this Z is any vector. This is what we know. So those were those X Zs. In general, we had here G and we had here G. So we had GB, GA minus identity Z. And we use this now for specific G for A plus. And what we want to show, if we are trying to show that this A plus B has the smallest norm among all solutions. So what we want to show is that the norm of A plus B is smaller than the norm of XZ. This is what we are trying to prove for all Zs. And now everything which remains is computation. So what remains is computation verifying this fact. Okay, and that we spare some time and we can prove also the other theorem. I won't do it very slowly, but let's go over the handouts and I will comment on the most important steps in this calculation. So I will just share handouts. Okay, this is on page 18. Okay, so this is what we are trying to prove. So A plus B, norm of A plus B is smaller than the norm of any other solution. And here we use the same as we did in the first hour. So how to express the norm of the vector. The norm of the vector squared is just this vector transposed times this vector. So square of the norm of the vector is just sum of squares of the components, but it's just this vector transposed times this vector. So this is what we use, what I used here in the second line. And then I transpose the first vector. So I get in the third line, I get A plus B transpose. In fact, in the third line, I already did all the computations. So what I do, I transpose A plus B, and then I transpose the second part, A plus A minus identity Z transpose. And then I have, in the first bracket, I have two vectors. And then in the two row vectors, and then in the second bracket, I have two column vectors. So I have to multiply each component, each vector from the first bracket with each vector from the second bracket. So, and I get 4 summands. So I get this A plus B transpose times A plus B. This is, I took the first components of both brackets. Then I have A plus B times the second vector from the second bracket. And then I do the same. So I take the second component of the first bracket and the first component of the second bracket. But since V transpose U is just a real number, I get the same real number again. So V transpose U and U transpose V is the same real number. So if I transpose V transpose U, then I get U transpose V. So it's the same real number. That's why I have 2 times this real number. And plus, then I have second components of both brackets. And what I notice in the third line, the first summand is just norm squared of A plus B. The third summand is just norm of A plus A minus identity Z squared. And in the middle, I get this real number A plus B transpose, A plus A minus identity. So, and what I want to show is that the sum of those 3 summands is bigger than the first summand. So this sum should be bigger than norm of A plus B squared. If I'm able to prove that this second summand is equal to 0, I'm done, because the third summand is square of a norm, which is positive. So it remains just to check that this second summand is equal to 0. And this is a short computation, and it uses the property of the Moore-Penrose inverse. So it uses, I think, that 2 properties of the Moore-Penrose inverse. So you can look at this computation by yourself, but it only it only uses the fact that A plus A that the A plus is a Moore-Penrose inverse of A in the calculation. And this is basically the end of the proof. So the norm of xz is bigger than the norm of this first summand. So A plus B is really the solution of smallest norm. Okay, so page 18 of handouts. And let's just try to prove the second theorem. Just the idea, and I will tell you. So I will tell you what's the main idea, and for the exact computation again, you can look at the handouts. So proof of theorem 2. In this theorem, we have AX is B, where N is bigger than M. And B is not in the column space of A. But we claim that X is equal to A plus B is the solution which minimizes sum of squares of the differences in the components. So is the solution with the method of least squares. Meaning that A times A plus B minus B is smaller or equal to AX minus B, norm of AX minus B for every X. So this is what we want to prove. We plug in, for X, we plug in A plus B. And we try to prove that A plus B minus B is then smaller, the norm of this vector is smaller than the norm of any other vector AX minus B. I will only show you one possible way how to prove it. So One possible way is to use the CVD decomposition of A. So let A be equal to U and then sigma V transpose. And then we know that A plus is V sigma plus U. And then we plug this into our equation, our star. And what we get if you compute the left part, again, you can, I will write where in the handout you can see precisely the computation. But if you compute this left hand side of star, you get at some point you get so you get U sigma V transpose. In fact, if you calculate this, let's say if you calculate the right hand side, AX minus B, you get U sigma V transpose X minus B. And then here you can use that since U is an orthogonal transformation, it doesn't change the norm of the vector. U transpose X, norm of U transpose X is equal to X, since U is orthogonal. And you get sigma V transpose X minus U transpose B. And here, if you use our decomposition V onto V1, V2 blocks, and U into U1, U2 block, this is the composition in the algorithm from the first hour. What you plug this V1, V2, U1, U2 into this norm, and what you get is C V1, and of course sigma is S0, 0, 0. You get S V1 transpose X minus U1 transpose B, and on the other component U2 transpose B. This is what I got when I just plugged in V1, V2, U1, U2 into this norm calculation. And now if we look at this vector which we obtain, we see that the second component of this vector, we don't have any impact on this component with our X. Whatever we plug in for X, we cannot change this second component. So this second component will be the same for every X. But what we could try to do is to kill the first component. So we choose such X to kill the first component. And the appropriate choice for X is just so S V1 transpose X minus U1 transpose B should be 0. We express X out of this and get exactly that X is equal to A plus B. So with the choice X is equal to A plus B, we can kill the first component, so it's 0, but the other is the same for all X's. So that this means that the solution with this, which minimizes the difference between AX and B, is exactly the one that kills the first component of this vector, and this is X is equal to A plus B. Kills the first few components. So you can look at the precise computation on page 23 of handouts. And there are also examples, so numerical examples. Okay, let's stop for today.